welcome to the course on coding theory. I am Adrish Banerjee from IIT Kanpur. Today we are going to talk about basic introduction to what coding theory is all about. So we will start our lecture. So in the introduction, as I said, we will talk about what is coding theory. We will illustrate with a very simple example how error correcting codes can be used for error detection and error correction. Before I start my lecture, I would like to talk about the books that we are going to use for this course. So we are going to follow this book, Error Control Coding by Lin and Costello. It's the second edition of this book. We are going to follow this book as our textbook. And there are some very nice books which you can use as a reference book. For example, this book by Sloan and McWilliams is a very nice book on block codes. You could also follow this book by Blayhood on algebraic codes for data transmission. This book, Error Control Coding by Todd K. Moon, this also gives a very nice introduction to error correcting codes. Or you could use this book by Huffman and Pless called Fundamentals of Error Control Codes. So when we talk about communications, communications basically involves three basic steps. The first is encoding a message. You have a message source that you want to represent efficiently. Now you can, for example, consider a speech signal. Now if you want to transmit a speech signal, you first have to convert your analog signal to digital signal, and then you need to get rid of useless redundancies. Why? Because we want to transmit basically useful information at the we want a source inherently has lot of redundancy, and when we try to represent a source, we would like to represent the source efficiently in minimum number of possible bits. So first step involved in any communication is basically encoding a message. Second is, once you have represented your source, you want to transmit that source over a communication channel. So the second thing is transmission of the message through a communication channel. And finally, once the receiver received the message, it has to decode to find out what was the information that was transmitted. So broadly, there are three steps involved in communication: encoding, transmission, and then finally decoding. So information theory basically gives us fundamental limits of what is the maximum limit of, like, what's the best compression, fundamental limit on compression that we can achieve. It also gives us fundamental limits on what is the maximum transmission rate possible over a communication channel. So let's spend some time on what is our transmission medium. So the transmission medium over which we want to send a packet, that is known as channel, and here I have illustrated two very simple channel models. The first, which is binary symmetric channel. Now you can see it has binary inputs, zeros and 1, and similarly it has binary output 0 and 1. Now with probability 1 minus epsilon, basically whatever you transmit is received correctly at the receiver. So this is a transmitter and this is the receiver side. So if you transmit 0 with probability 1 minus epsilon, you will receive it correctly. Similarly, if you transmit 1 with probability 1 minus epsilon, you will receive it correctly, and this crossover probability of error is basically given by epsilon. So this is basically a symmetric channel, and it's a binary channel because the binary input, binary output is known as binary symmetric channel. Another channel which basically is very commonly used to model packet data networks is what is known as binary erasure channel. So there are binary inputs, zeros and ones, and the outputs are either you receive whatever has been transmitted, you receive it correctly, or whatever you have transmitted is basically erased. So this delta that you see, basically we are denoting an erased bit using this symbol. So with probability 1 minus delta, you receive the bit correctly, and with probability delta the bit is erased or lost. So, in his landmark paper in 1948, Shannon introduced this concept of channel capacity, that what is the maximum rate at which we can communicate over a communication link. So, a channel capacity is defined as the maximum amount of information that can be conveyed from the input to the output of a channel. Shannon in his theorem also proved that there exist channel coding schemes that can achieve very low, arbitrary very low probability of error as long as the transmission rate is below channel capacity. So, Shannon showed that there exists good channel codes, so as long as the transmission rate is below channel capacity, we can achieve arbitrarily low probability of error. For example, if we talk about channel capacity of a particular link to be 2 gigabits per second, then basically we should be able to communicate at any rate up to 2 gigabits over this communication link without basically, and it can achieve very low probability of error at the decoder. Now, in his theorem, Shannon did not specify how to design such codes which have rate close to capacity, and that is where basically error control coding comes into picture. So, the goal of error correcting coding theorists is to achieve this, to design codes which can achieve this limit. So, basically Shannon has mentioned that we could transmit, we could design, as long as we design error correcting codes which have rate less than channel capacity, we can achieve arbitrarily low probability of error. So, the goal of the coding theory or of error control coding is to design such error correcting codes with rates as close to capacity which can achieve arbitrarily low probability of error. And Shannon did not specify how to design such codes. So, basically where coding theorists come into picture. So, how do we design an error correcting code? An error correcting code is designed by adding some redundant bits to your message bits. The message bits we call them information bits, and those additional redundant bits that we add, those are known as parity bits. So, error correcting code is designed by properly adding some redundant bits to your message bit and then send this coded message over a communication link. Now, we use these additional redundant bits to detect error and to correct error. Error correcting codes has wide range of applications in digital communication and storage. I have listed basically a few of the uses. For example, when we send a signal over communication link, it's get corrupted by noise, fading, interference. So, to combat the effect of all these, basically we use error correcting codes to correct the errors. Similarly, in digital storage system, you want to correct the error caused due to storage media defects, dust particles, radiations, we use error correcting codes there. So, let us take a very simple example of error correcting codes and illustrate how we can use error correcting codes to detect and correct errors. So, the example I am going to show you right now is of what is known as repetition code. So, the rate is defined as the ratio of number of information bits to number of coded bits. So, when I say rate 1/2 code, I mean there is one information bit or one message bit and there are two coded bits. For example, in a repetition code, in a binary repetition code, basically we repeat whatever is the information bit is. So, a rate half repetition code would look like this. A binary rate half repetition code would look something like this. So, for 0 we would be transmitting 0 0, and for 1 we would be transmitting 1 1. Similarly, for a rate 1/3 repetition code, For 0 we will be transmitting 0 0 0, and for 1 we will be transmitting 1 1 1. So, you can see here in this, in rate 1/2 case, we are adding one additional redundant bit, and in case of rate 1/3 code, basically we are adding two additional redundant bits. Now, how we are going to make use of these redundant bits for error correction and error detection, that will be explained in the next slide. So, let us take this example. Let us say I want to transmit these set of bits. So, I want to transmit 0 0 1 1 0 1. Now, if I use a rate 1/2 repetition code, what would be my coded bits? For 0 I will be transmitting 0 0, for 0 I will be encoding them as 0 0, for 1 I will be encoding them as 1 1, and for 1 I will be sending them as 1 1, for 0 I will be sending as 0 0, and for 1 I will be sending as 1 1. So, this will be my coded sequence. Okay. Now, here I have illustrated one case where there is a single error. So, this was basically the sequence which was transmitted. Think of it that this sequence has been transmitted over a binary symmetric channel, and this is what the received sequence I received. So, you can see here this is a case of a single error. The first bit which was transmitted as 0 was received as 1. Now, how can I use error correcting codes to detect error? So, since it is a rate 1/2 code, for each information bit I am sending 2 coded bits. So, at the receiver I will look at 2 bits at a time. So, I will look at, first I will look at this 1 0. Now, since it is a repetition code, what do you expect? I expect that both the bits should be same, right? But here in this case, first bit is 1, second bit is 0, which means there is a transmission error. So, I am able to detect single error. How? Because these bits were encoded using rate 1/2 repetition code, I expect these 2 bits to be same. So, I know there is an error in the first bit, but I do not know whether this is bit 0 or bit 1. Let us look at other received bits. 0 0, this will be decoded as 0, 1 1, this will be decoded as 1, 1 1, this will be decoded as 1, there is no ambiguity, 0 0, this will be decoded as 0, again there is no ambiguity, and 1 1, this will be decoded as 1. So, we can see that using one additional redundant bit, we are able to detect single error. Now, let us look at example for double error. So, let us say the first and second bit are received in error. So, what we have received is basically 1 1 0 0 1 1 1 1 0 0 1 1. So, the first 2 received bits are in error 1 1. Now, let us see whether we can detect error using this rate 1/2 repetition code. So, again we will follow the same logic for decoding, we will look at 2 bits at a time. So, first 2 bits are 1 1. Now, since these bits are same, we will decode them as 1, but what was transmitted? It was 0. So, we can see that this is a case of undetected error. Even though these 2 bits were received in error, the decoder is not able to detect this error. So, this kind of thing happens when the error pattern is such that it transforms one code word into some other code word. So, since 1 1 is a valid code word for 1, the decoder is not able to detect this error. So, this rate 1/2 repetition code is able to detect single error, but it is not able to detect double errors. Now let us look at whether it can correct any errors. So let us look at this example when we had single error. So note here, so what we received was 1 0. So we were able to detect error, that there was an error, but can we correct it? No, we cannot. Why? It is equally likely that this 1 that we received was 0, or this 0 that we received was 1, if we are talking about a binary symmetric channel, right. So we do not know whether the first bit got flipped to 0, first bit got flipped to 1 instead of 0, or the second bit got flipped to 0 instead of being 1. So this particular rate half repetition code cannot correct any errors. It can only detect single errors. Now let us look at another example. This time we are considering a rate 1/3 repetition code. So what does rate 1/3 repetition code means? For each, and again we are considering binary code, so for each bit we are adding, so 2 parity bits, and we are repeating the same bit. So for 0 we will be transmitting, we will be coding it as 0 0 0, for 1 we will be coding it as 1 1 1. So again we consider the same example of transmitting 0 0 1 1 0 1. So we are transmitting the same information sequence. This time we are encoding them using rate 1/3 repetition code. So this 0 will be encoded as 0 0 0. Similarly 1 will be encoded as 1 1 1. So we will be transmitting this, so this information sequence will be coded in this particular way. Now we will again look at what happens when there are errors in the receive sequence, like we did for rate 1/2 repetition code. So let us again look at the example for single error scenario. So let us say the first bit was received in error, so instead of 0 we received a 1. Now let us see whether our rate 1/3 repetition code can detect single error. So since it is a rate 1/3 code, for each information bit we are sending 3 coded bits. So we are going at the receiver, we are going to look at 3 bits at a time. At the decoder we are going to look at 3 bits at a time. So we will first look at these 3 bits 1 0 0. Now what do we expect? We expect, since we are using a repetition code, we expect all these 3 bits to be same, but here in this case they are not, because what we have received is 1 0 0. Now what does that mean? That means there is a transmission error. So we are able to detect single error using a rate 1/3 repetition code. If we look at other sets of bits, 0 0 0, there is no error here, 1 1 1, no error, again no error here, no error here, no error here. So rate 1/2 repetition code was able to detect single error, even rate 1/3 code is also able to detect single error. Now let us look at double error. So let us consider a scenario when the first 2 bits are received in error. So we have 1 1 and rest of the sequence is this. Okay. Now can we detect double error? So let us look at, we again look at 3 bits at a time. So if you look at 3 bits at a time, the first 3 bits are 1 1 0. Now we could see that there is an error. Why? Because either this should have been 0 0 0 or 1 1 1, but we received 1 1 0. So we are able to detect using rate 1/3 repetition code, we are able to detect double errors as well, which we were not able to detect using rate 1/2 repetition code. Now let us look at the error correcting capability of this code. So let us go back again and look at single error situation. Now when the single error happens, so something like this, let us say one of the bit got flipped 100. Now can we correct single errors? And the answer in this case is yes. Why? Because if you look at these 3 bits, 2 bits are already 0 and 1 bit is 1. So it is, and what are the possible outcomes? This could be either 000 or 111, and it is more likely that 1 bit got flipped. It is more likely that 0 got flipped to 1 rather than 2 zeros, 2 ones getting flipped to 0. So it is more likely that this bit got flipped from 0 to 1 instead of these 2 bits getting flipped from 1 to 0. So using majority logic, since majority of the bits are 0, we will decode this as 0. So we can see this rate 1/3 repetition code can correct single error. This was not possible for rate 1/2 repetition code. Now can it correct double errors? Now if we look at this 110, it will think that this particular bit got flipped from 1 to 0, so it will decode this as 1. So this cannot correct double errors. So to summarize, we saw that rate 1/2 repetition code can detect single error, but cannot correct single error. It cannot detect double errors, whereas rate 1/3 repetition code can correct single error and can detect single error. It can detect double error, but it cannot correct double errors. So why is this code better than the first code? It has certainly has better error detecting capability than the rate 1/2 code. This we will discuss in subsequent lecture. It has to do with separation between the distance separation between the code words, and you can see basically in this particular code we are using 2 redundant bits, and in the previous case we were just using 1 redundant bit. So the error correcting capability and error detecting capability of the code is dependent on the distance properties of the code, and that we will talk about in subsequent lectures. So to summarize it, I think this quotation by Solomon Gollum rightly captures what error correcting code is all about. So I will read it. A message of content and clarity has got to be quite a rarity. To combat the terror of serious error, use bits of appropriate parity. Thank you.